Hello, this is Questionable Coding with Vladimir, and today we're going to talk about an extremely important topic called graph. Graph is a data structure that is almost always used during technical interviews, and it's widely used in production code for different algorithms. So we'll start with a general description. We'll cover different types of graphs, common problems, how we can implement a few of the methods in JavaScript, and many more. So let's start. So what's a graph? Graph consists of nodes or vertices connected by edges. It's a very simple concept, but it describes a lot of what's going on in the real world. The most famous example is a social graph, where we have a connection between people. And on the picture you see 5 blue nodes, each representing a person, and some people are connected with others by edges. So it means that Vova is connected to Tim, and it's an undirected graph. Tim is connected to Vova in return. So let's check all the types. On the previous picture you saw an undirected graph, where every connection is mutual. But imagine every node is a crossroad, and every edge is a street. Some streets are one-directed for traffic. So this relation should be a directed relation. And if we want to take a shortest path between two crossroads, we need to take this into consideration. There is a separate class of problems and algorithms that are devoted to a directed graph. Another type of graph is a weighted graph. It also has its own set of problems. So imagine every edge, it can be directed or non-directed, has its weight. Weight is some resource that we consume when we throw some price to travel from one place to another. It can be fuel, it can be time, it can be anything. So what we want to do, we want to take those weights into consideration. So the shortest path, not always the path that requires less nodes than some other. It should take into consideration the sum of weights that are assigned to edges. There are also cyclic graphs where you can find cycles, and a node can point to itself, and it explains different types of relations. So there are many more classifications of graphs, for example, full and sparse graphs, but you better check it on your own. Let's cover common problems with graphs. For example, minimum spawning tree problem. So, for example, you have several buildings and you want to connect them into a network. You can use a lot of connections here, a lot of edges, but we want the smallest network we can afford. So the question is how many edges and what edges you should use to connect all the houses. And yeah, that's a very common problem. Also clustering. If you have a number of nodes and you want to understand what clusters do they form, are they separate, do they form one graph, or it's like a separate smaller graphs? Topological sort is another famous problem. So for example, you have some course, React course, and you want to learn some prerequisites for that. So one of the prerequisites can be learning web basics, learning JavaScript, learning algorithms, and you want to check in which order you need to pass those prerequisites. So in this case, I already put numbers, appropriate numbers for that. First we go to 1, then we go to second node, to the third one, to the fourth, and to the fifth. There can be a different topological sort. We can, for example, go first to 1, then to 2, to 4, to 5, and then to 3. And it will also be enough for us to learn what we need in the end. Another problem, I think the most famous problem with graphs is finding the shortest path. For example, we have a big graph, some connections, roads, or anything else, a social graph. We have node A, and we want to see how can we quickly reach node B. And this algorithm, this set of problems, they describe how to calculate this shortest path. Representation. So we have several ways to represent graph in code. The most famous are matrix, adjacency matrix, and adjacency list. Let's talk about matrix. So imagine we have nodes, a matrix of nodes, and we describe connections when they intersect, when rows intersect with columns. For example, if Tim is connected to Vova, Anne, and Lee, we put true in these squares. So the problem is that we require a lot of memory for that. We have n nodes, we need n squared memory to keep all these flags true, false, And for most of the graphs, it's too much because there are not so many edges that, not so many nodes that are really connected, and we have several truths in this matrix, and all other squares will be false. It's not very efficient. If we want to add one more node, we need another row and another column, which is a lot. But the lookup is very fast. The list gives us another idea. We have a map where the key is our node and the value is a list of connections. So it's much more space efficient. We don't keep false values, false flags where we don't have a connection, but the lookup is not that fast because you need to find the node. It's easy in the map. It's big O of 1, and then you check all the list if there is a specific node connected to our key. Graph operations. They're pretty standard. So standard are node, add node, remove node, add edge, remove edge, and contains an element. Optional is empty, size, and merge two graphs. But what we're interested in is traversal methods. So we have BFS and DFS. BFS stands for breadth first search and DFS depth first search. Let's take a closer look. So now we're going to visualize traversal algorithms using a resource called Graph Online. I really recommend this resource to visualize graph, to play with them. And first we'll go through breadth first search. It's quite easy to understand. We'll pick an initial node, let's say 2, and it will check for all the neighbors of this node. It will be neighbor 1, 3, 6, 7, and it will add them to a queue and then check all the neighbors of these nodes. So it will be 0, 12, 11, 10, 9, 4, and they will be also added to a queue, and that will go on until all the nodes are visited. So at some point, going from this initial node, on some level we'll find our node that we search for example 13. So I'm pressing and we're just watching how it's filled and visited. Another approach is to use depth first search. It's different. So here we don't go layer by layer, but we're going as deep as we can. So it went to 1, 0, 12, 11, 10, 5, 9, and when it reached the very end, it returned and continued with some other node that it didn't visit before. So it's completely different, and these two methods are used for different things. Usually for finding shortest path you will use breadth first search, the first one. But please check both because they are applied in different cases. Now let's talk about the complexity, keeping in mind that we're using adjacency list, not the matrix. So to add a node, we just don't spend anything. We don't need to create another column and row as in matrix. We just add them to the map. When we want to add edge, it's also not a problem. So we just find the key in the map, find the appropriate node, and then we add an edge. To remove node and to remove edge, it will be more complex. So if we want to remove a node, we first need to remove the node and its edges, and then check every other node if it's connected to the node we want to remove. So we'll have to check all nodes plus all edges. To remove an edge, we just need to check edges because we know the node that we are working with. Okay, let's try to code the graph. So I already made some preparations, and we have a graph class, and we have a private property nodes. And in constructor, we'll fill nodes with an empty object. So it will be a map. That's why object is pretty helpful here. We have a simple function called add node. We're passing a node, which will be a string. We don't need a fancy node, not an object. The string is enough. So we're filling this map with our first node, or not first, of course, this method can be called as many times as we want. And for each new node, we assign a new and empty array. this array will hold all the edges of the node. And we have a function called addEdge. It's a bit more complex, but nothing special here. So first of all, we are checking if our node, we have two nodes here, source and destination. That's how we create an edge between them. So at first we check that if they are not in the list of nodes in this map, then we won't continue, because it doesn't make sense to have an edge between something that doesn't exist in the map. So we're doing this check for source and for destination node. And then we have a similar calls for adding this source or destination node to our edges. So at first we check that a specific node doesn't have destination like that, like we passed. And in this case, we push this destination to the list of connected nodes. And we're doing the same for destination. So we are having an undirected graph. It means that when we add an edge for one node from one node to another, we need to add an edge from the second node to the first one, because we're working with like bidirectional connection. And that's basically it. It will allow us to create a proper graph. So what I wrote here is a text representation of a graph we want to achieve. So we have several nodes connected to each other in this way. I think it's quite obvious. And I create an instance of a graph, and I'm adding nodes, every node, and I'm adding edges. So it's like a shortcut. When we add a node from Vova to team, we automatically add an edge from team to Vova. So the amount of adEdge calls is not that big. And then I'm running a function called showNodes. It's not implemented here. Let's do it to just show our nodes on the screen. It will be just a console log of a private property. Since it's private, we can't reach it from the outside. And that's all. So let's execute the function. And here we have this adjacency list as we discussed it during the theory part. Okay, we're done with this part. Now we're going to implement a breadth first search. For that, I'll uncomment the call, and we'll try to implement the method itself. Okay, let's try to execute the BFS function. It will show us a path if it exists or not. We can make it more complex to show the path or show the number of steps we use to reach some node, but we will keep it simple. So the signature is source node and destination node. We'll have a queue, and it will be initiated with an array with source. So it's our starting point. And we'll have a visited, it's a map called visited, where we'll keep the status of all visited nodes. We don't want to check any node twice. Then we'll continue, we'll return false if nothing good will happen. But before that, we're going to run a while loop, where we have something in the queue. I'm going to run the following code. And first we're going to grab the current element. It's the most left element in the array. So it's just the top element on the queue. Let's put it like that. So queue shift. Now we're going to check if it was already visited or not. If visited has this key, then we don't want to continue. We'll just, in fact, we will continue, but we won't run the rest of the code in the loop. We'll just continue to the next loop element. Then we're going to check if this current element is equal to our destination node, because if yes, then we'll just return true. It's our end goal. And if it didn't happen, we'll mark it as visited. The only thing we need to do, I think it's the main step here. So we need to grab all the neighbors of our element, and we're going to use our map, this node map, for the current element. For each neighbor, I'm using a simple for loop here, but you can use any loop you have or you prefer. So for every neighbor, we're gonna add every neighbor to our queue. Okay, that should work. So I have a method running it. It's called BFS, and it uses Tim and Jeff, which are there in the graph. So let's launch it. And we have false. So we expect it to be true, so there is an error somewhere. Let's try to find an error. So we have a queue, we initialize it with a source, then we have an empty visited map, while queue length. We shift the first element of the queue, check if it's visited, we check if it equals destination, we mark it as visited, and we grab all the neighbors, and for every neighbor we push neighbor to the queue. Yeah, that's an error. Of course, we should use an I, not 0. And we have true here. So that's perfect. And that's how we implement BFS. I also decided to implement a DFS, and I don't want to do it live. I'll just explain, for the sake of time, I'll just explain how it's executed. So DFS is different. We're not searching the neighbors of every node. We are going as deep as we can. So it's a recursive approach. We have a DFS function, which has source, destination, same as before, and we have a visited array on a map that we pass on iterative calls. So at first, it's our base case. If our node is visited, then we'll return false. We don't want to work with a visited node. If source equals destination, we'll return true. And after that, if it didn't happen, we say that visited source equals true, not to visit it again. And we're also taking neighbors and iterating through neighbors. But for every neighbor, we have a DFS function. And instead of going through every neighbor and adding it to a queue, we, on every step, go deeper and deeper here. And only in case we'll face true somewhere, so we found the node, we return this true all over and over again. And if nothing of that worked, we return false. So the recursive approach may be complex for people who are not familiar with recursion, but in fact, if you can follow such code flow, then it's not a problem for you. So please practice with the recursion, because it's essential for implementing DFS. And that's it. So I recommend to spend a lot of time in graphs. You'll probably face a lot of this topic during interviews and probably at your work. So please just spend a little time on every type of task that is there for graphs, like topological sort, creating spawning tree, breadth first search, depth first search, and others, to have an idea of how to deal with graphs, where to use them, and how to solve them efficiently. So stay tuned, please subscribe, and I hope you like it.